Okay, thanks. Okay, I have to share my screen. So let's see. Okay, is that visible now? Okay, let's see. Let's make it full screen.
Yeah, that's visible.
Okay. Okay, there we go. Now it's full screen. Okay, great. So yeah, thanks for the invitation to speak here, and thanks for letting me do this online. Appreciate it. So yeah, so without further ado, this is joint work with Agniva Dasgupta and Winghong Joseph Lung. Did I see Agniva in the audience? Is that yeah? I see us. Yeah, I see you waving. Yeah, hi Agniva. I hope you're doing well. Yeah, so I was really disappointed I wasn't able to come to this conference. I wanted to visit India, but I just couldn't do it with some family health problems. So okay, so let's just start. So here's some, I guess, some motivation for like a kind of a broad audience. One of the questions that we're interested in is what's the distribution of the Riemann zeta function on the critical line? So for fun, I plotted, so this is a plot of the Hardy Z function. So the Hardy Z function is, so it has the same absolute value as the Riemann zeta function, except that it's real valued on the real line. And so, so this is basically a plot of how zeta behaves on the critical line, just rotated so that it's real valued. And okay, so this is zeta, or z. This is plotted up to 30. Here's another plot up to 100. You can see like it's kind of wiggly and not very large. Here it is up to 1,000. It doesn't really get above 10, and again it's still pretty oscillatory. And then here it is up to 10,000, and it's a little bit bigger, but like we see some peaks. Like here it might be close to -15 down there, but yeah, so not very large. And so so we have some ideas of that make us think that we know what's going on. So there's the Lindelof hypothesis. So it states that the zeta function does not grow faster than any small power of t. So this is known to follow from the Riemann hypothesis, but nevertheless it seems to be very hard to prove, and there's been a lot of work to try to attack this question. And yes, I'm sure there have been lots of talks that have something to do with this, but okay. So I wanted to talk some more about moments of the zeta function. This is just as our kind of way to get into this this question. So in 1918, Hardy and Littlewood proved an asymptotic formula for the second moment, showing that it's size t log t. And then in 1926, Ingham showed asymptotic for the fourth moment, which grows like t log t to the fourth. And the sixth moment is still wide open. That would be a sensation if anyone could get an asymptotic or even a good upper bound on the sixth moment. So this is almost 100 years from Ingham's fourth moment, and we're stuck on 6. We've been stuck for a very long time. So okay, so what do we know about the maximal size? So we have the Fragment-Lindelof convexity principle, which is a variant of the maximum modulus principle, and it implies the convexity bound, which says that the zeta function is bounded by basically t to the 1/4 for t large. So as the first improvement on this convexity bound, Hardy and Littlewood used Weyl's differencing method to show this bound of t to the 1/6, which we now call the Weyl bound. So there have been a lot of various so one, there's a lot of improvements on the bound. The current record is due to Jean Bourgain. There are also a lot of alternative proofs of this bound, this Weil bound t to the 1/6. I'll mention some of those in some upcoming slides. So this exponent 1/6 reoccurs a lot. There's like a lot, there are a number of moment-based approaches to understanding the zeta function, and a lot of these moment approaches lead naturally to this exponent 1/6. So, and it occurs in a lot of other problems or other types of L functions where, so it's just this exponent 1/6. It occurs a lot, and we call it the Weil bound. Okay, so we can use moments to deduce subconvexity in many situations. So one of the first results I know about this is so there's a formula, their paper of Atkinson from 1949, and he developed this sort of exact formula for the second moment of zeta with some weight function, and Heath-Brown used Atkinson's formula. This was a 1978 paper, and he used Atkinson's formula to get an upper bound on the second moment of zeta in a short interval. So for this case, it's the length of the interval. The shortest interval he could get was, using this approach, was t to the 1/3, and then it's Lindelof on average over that interval. And so, I don't know why there's like this 30-year gap from Atkinson's paper to Heath-Brown, but this was the best I could do in terms of figuring out the short second moment of zeta. But maybe maybe someone knows another reference. And that, because Heath-Brown's work is like a pretty straightforward extension of what Atkinson did. So it's kind of surprising it took 30 years for that to happen, but maybe I just don't know the history that well. So then for the fourth moment, Ivanets in 1980 proved a short fourth moment estimate. So in this case, the interval is longer than in the second moment. So this is a length t to the 2/3. But the moment is higher, so it's a fourth moment. And so again, he was able to get this short fourth moment in this case, which is consistent with the Lindelof hypothesis on average. Both of these results can be used to prove that the zeta function is bounded by t to the 1/6. I guess as a heuristic, you might think that if the zeta function is large at a point, it has to stay large, at least for a little while, almost size like 1 or maybe 1 over log t or something like that. And so then that's how you can leverage a moment bound into a pointwise bound. And so you can, so each of these bounds then turns into a pointwise bound giving you the Weil bound. But the moment gives you more information than just the subconvexity bound, because it gives you more information about like the measure of the set on which your function can be large. Okay. So there are results on higher moments as well. A well-known example is the 12th moment of zeta. So Heath-Brown in the same paper from 1978, and also Ivanets in that paper from 1980, they both were able to prove this 12th moment bound, so in this case, the exponent is not consistent with Lindelof. It's bigger by a factor of t. But since it's still like a really high power moment, like in this case 12th moment, nevertheless, even though it's not like a Lindelof consistent bound, you can still get strong results from this, and in fact you can get the Weil bound from this bound as well. And so Heath-Brown's paper, or his method, uses these short second moments that I listed on the previous slide, and then Ivanets also got this 12th moment bound using the 4th moment instead. So these shorter versions of the low moments were used to give information about the higher power moment. So from the 4th and 12th moments, we can interpolate these exponents. So you can use Holder's inequality. So if we start with 6, it's like you can cook up a Holder's inequality to balance this between a 4th moment and a 12th moment with some exponents, and you just do the calculation, and the bound you get from this kind of interpolation is t to the 5 over 4. And so this is the strongest result that we know about the 6th moment of zeta. Okay, so that's where we're stuck. Great. So now let's talk about an analogy. So I want to talk about like GL2 versions of the problem. So shifting away from zeta to more general setting. So let's take F to be a Hecke-Kuss form for let's say a congruence subgroup of SL2Z. You might just take it to be SL2Z. Suppose it has this Fourier expansion. So let's assume F is a holomorphic modular form, just to make this a little bit easier to write down the formula. So then we have this Fourier expansion. So I like to use lambda f of n times n to the k minus 1 over 2 as my Fourier coefficients. And so lambda f of n's have the property that they're bounded by the divisor function using Deline's bound. Okay, and let's also Hecke normalize it so that lambda f of 1 is equal to 1. So then, great, so then we have this, so you take this Dirichlet series with these coefficients, your lambdas, lambda of n's over n to the s, and then this is a degree 2 L function, and if f is a Kuss form, then this is a sort of irreducible L function. It does not factor into degree 1 L functions. But so many of these properties of this degree 2L function you can relate or in a way are similar to just the square of the zeta function. So you take zeta function squared, the coefficients are the divisor function. You can think of this as zeta squared as a GL2L function, but with an Eisenstein series instead of a Kuss form. So generally, if you have an Eisenstein series for your automorphic form, then the associated L function will factor into lower degree L functions. Right, and so zeta squared behaves like this Kuss form, but the difference is that zeta squared is factors into 2 degree 1 L functions. It's kind of obvious by the way I've expressed it, but yeah. So if you want to compare a degree 2 L function to other things, like you should compare it to zeta squared. Okay, so lots of things are similar, but lots of things are also different. But so here's a similarity. So Anton Good in 1982 showed a short second moment for this degree 2 L function. So he was able to get length t to the 2/3. And so this should be like a lot like Ivanitz's 4th moment result. So this L function we should think of as like zeta squared, and so in total this is like zeta to the 4th. And it's similar in quality to Ivanitz's result, and then this also can be used to deduce subconvexity for this degree 2 L function in the t aspect. Okay, so similarly, we can think of zeta cubed as the L function for a GL3 Eisenstein series. And so then like these questions about the 6th moment of zeta are the same as like the 2nd moment of this degree 3 L function, whereas it turns out to be where it happens to be an Eisenstein series on GL3. And then we can do the same sort of exercise that we just talked about with like Anton Good's result. So we can also consider what happens if you take a GL3 Kuss form. So what's a degree 3 cusp form? So the existence is a lot more non-trivial than for the degree 2 case. But here's one way to cook up an example. So again, start with our Hecke cusp form for SL2Z. If you want, you could just take the Ramanujan delta function of weight 12, and okay, so we still have the same Fourier expansion as on the previous slide. So there's a symmetric square lift of f, which you can write down very explicitly in terms of the Fourier expansion. So you just write down this Dirichlet series. So you're basically sampling your coefficients on squares, although you have this extra like m squared to the s that's kind of like sort of looks like a zeta of 2s, but you don't really want to factor it that way. So this Dirichlet series that I just wrote down, this is a genuine degree 3 L function. So these are the certainly the simplest degree 3 L functions, like irreducible L functions, that we can write down. Although the fact that this is a honest to goodness L function is very non-trivial, but I don't want to get into that aspect of things. So just for fun, I went to the LMFDB and the L function modular form database, and it has some degree 3 L functions, and it's in the database, and the first one in their list looks like this. And so these are all approximations to the coefficient. So there's this is not an exact formula. So this is not negative 0.421. There's like additional digits. Presumably this is some kind of complicated transcendental number, but we don't know anything about that. But anyway, you have some sort of a Dirichlet series. We have some gamma factor, and this is a degree 3 L function. And here's a plot of it, this is a plot of the sort of the generalized Hardy Z function for that L function. So this has the same absolute value as the L function, but is real valued. So one thing that happens here is that this is not symmetric or it's not an even function of t, and that's related to the fact that this is not a self-dual L function. And so the functional equation relates this L function and its dual, and those are different L functions, and so there's nothing that's forcing this to be even. Great. So that's just a fun example. So this is supposed to, this was just for fun. So now I can state our main theorem. So suppose you have a fixed cusp form on SL3Z, then we were able to get a bound on the second moment of this degree 3 L function, which is the upper bound is t to the 4/3 plus epsilon. So we didn't actually check this, but I'm sure it's true that you could also use the same method when for zeta, for the 6th moment of zeta. And this would give the bound it'd give the same bound t to the 4/3. So one reason we didn't bother to do this is that the exponent that you get, so this 4/3, that's bigger than 5/4, and so we don't, you don't get a new bound on the 6th moment of zeta. Yeah, so that's fine. Okay, so that's fine. So, but for this degree 2 L function, or sorry, for the second moment of the degree 3 L function, like the actual so the cuspidal case, then we don't have these same tools that we did for zeta. There's no way to interpolate like a lower moment and a higher moment somehow. Like first of all, we don't have a higher moment available, but we also, like this is sort of the lowest moment that we can reasonably handle. And so the tools break down. So the tool that gives us t to the 5/4 for the sixth moment of zeta, like that's inaccessible for this problem. So that's just one comment here. So this bound is more interesting for in the cuspidal case than for the sixth moment of zeta case, like the Eisenstein case. Okay, so that's the main theorem. It's early in the morning here. Last week I was giving lectures last week, so some of you were there, but we changed the clocks in the US, and so now anyway, my point is I need my coffee. Maybe I should talk slower. I tend to talk pretty fast, so I think I have time. And if there are any questions, please feel free to interrupt and ask. Okay, so that's the main theorem. So just to help figure out what this is saying, or sort of judge the quality of this result, first thing to mention is that the analytic conductor of this degree 3 L function is like t cubed, or this extra 1 plus t cubed. Just like zeta, so the analytic conductor of zeta is t, and so this is degree 3, so this should be t cubed. And so the bound that you get, like the pointwise bound that you get from this is the conductor to the 2/9. The convexity bound would be 1/4. 2/9 is less than 1/4, so this gives a subconvexity result for this L function in the t aspect. So this is just to indicate that this is a non-trivial result. Another way to judge this is that so there's a very general tool for estimating moments of Dirichlet polynomials in the t aspect, and called the mean value theorem for Dirichlet polynomials. And for if you apply that very general tool to this particular problem, you get t to the 3/2 or plus epsilon. So this mean value theorem, okay, so it gives you something. So if you drop all but one term here, you just recover the convexity bound. So any improvement over the mean value theorem will give you a subconvexity bound, at least for this problem. So okay, so that's another way to judge this. So we improve on the mean value theorem. So our work heavily builds on some prior work on a closely related question. So this was by Keshav Agarwal, Winghang Lung, and Ritabrata Munshi. So they showed a short interval bound. So so this case, okay, so it's still the second moment. The length of the interval is t to the 2/3. So it's kind of like Ivaniewicz's length, this t to the 2/3. And then the bound that they got is t to the 5/4. So again, this is, okay, so this is a little harder to compare, I suppose, because it's a short interval. And so if you drop all but one term, in this problem you get the conductor to the 5/24, and this is the best known subconvexity result for these L functions in the t aspect. Okay, so I already mentioned this, so our work builds on this short interval method. So just to say more explicitly what bound they get, so they have this bound that is for t to t plus delta for some general delta, and then they get these four terms. I think I wrote the more important ones first, at least the important ones when delta is near t to the 2/3. So the first two are maybe the main ones. So right, and so if you optimize the bound, the best bound happens to occur when delta is t to the 2/3. So one of the things I was interested in, why I wanted to study this problem was I was puzzled why is this bound not good when delta is equal to t? So if you plug in delta equals t here, I didn't check recently, but I think you get a worse bound than the mean value theorem for Dirichlet polynomials. Let's see, is that true? yeah, like this bound delta cubed over t to the 21 over 20, that's pretty close to t squared when delta is equal to t. So that's way bigger than t to the 3 halves. Okay, so the bound is not good when delta equals t, but like in history, like if you think back to like my early history about the zeta function, the first works on the moments of the zeta function started with the long interval. They got the asymptotic in the long interval, and then it only took, and then it took like, you know, depends how you count, but like for the fourth moment, it took until, it went from 1926 to like 1978 or 1980 before we got a short interval bound. And then for the second moment, I mean, Atkinson maybe should have done it, but maybe it waited until Heath Brown. I don't know. So anyway, it took many decades to go from the long interval bound to the short interval bound, but here we just have the short interval bound, but not the long interval. So I was curious about this and wanted to know what was going on and to see if we could say something about the case when delta is equal to t. So there is some prior work on the delta equals t case. So Sam Purnapal showed in 2022 a non-trivial bound for the long moment, and so the savings was like 3 over 88 in his result. And so this is the first result that for the long interval that improves over the trivial bound. There's another result to mention. So this one's about zeta. This is due to Bayer, Browning, Marasinghe, and Zhao from 2012. And so they studied, maybe I'll say more about what they studied, but they studied averages of shifted convolution sums of the D3 divisor function. And so they got results on that. And then if you apply that method to the sixth moment of zeta, you get the bound t to the 11 over 8. So this is a non-trivial result, like it's less than 3 halves. It's bigger than the 5 over 4 that you get from interpolating the 12th moment. And also this is bigger than the 4 over 3. So whatever we're doing with to get 4 over 3 gives a better result than this 11 over 8. Great. So I wanted to say some words about the history of the subconvexity problem for GL3. Because it's not a really long history. There's a much longer history for GL2. I mean, maybe you've seen some of these things in some other talks. Yeah, the time zone difference makes it very difficult to participate in the US. Unfortunately, so I'm not sure exactly what all has been talked about. I looked at the the titles and the abstracts of the other talks. So the first subconvexity result for GL3 was a big breakthrough by Xiaoxing Li in 2011. Excuse me. So she studied this problem. So it's a GL3 cross GL2 problem. So she fixes like this sim square of f. So like you might again think of like the symmetric square of a Ramanujan delta function that's fixed once and for all. And then she sums over Moss forms. U sub j, uj is the Moss form, in summing over the spectral parameters in some kind of window, like a narrow window, and evaluates them at the central point 1/2. And then there's also like kind of an Eisenstein series component of this family that gives you a integral moment of the symmetric square L function on the critical line. And she was able to get a bound which is consistent with Lindelof. So the size of this family is around delta t by Weil's law. So this is consistent with Lindelof, and she was able to get delta as small as t to the 3 over 8. So in order to get subconvexity from this, you need to know that these central values here are non-negative. And for that, you need to know that this GL3 form here has to be self-dual, which means that it has to be a symmetric square. And so this only works for symmetric squares, but you get a strong result. And so she was able to get a good subconvexity result using this method. But the method doesn't work for non-self-dual GL3 cusp forms. So the first result getting subconvexity for those L functions was by Munshi in 2015. And he used a delta method that I'm sure has been discussed at this conference or workshop or whatever title we're giving to the title of this thing. So anyway, so he's using a delta method. It's not a moment bound. So various other authors subsequent to Xiaoxing Li have refined her method. And so the current state of the art is, so there's two papers I guess I mentioned. So there's a paper by Lin, Nunez, and Ji Qi. So this was kind of an approximate version of the formula. And then there's a paper by Humphreys and Kahn that got an exact formula. But basically these say that if you take Li's moment, then there's a main term of size delta. It's kind of like your diagonal term. And then there's a dual moment, kind of like a spectral reciprocity moment type thing. So there's a dual moment, and the dual moment essentially looks like the following thing. So you get, so it factors as a degree 1 times a degree 3. So you get zeta times this symmetric square. And you get a t integral of this thing. There's some kind of complicated weight function here. I think I've scaled it, so it's basically absolute value at most 1, and then, but it might be spinning around, might be quite oscillatory. But anyway, that's the structure of the dual moment. And so if you want to then get a good bound on this original problem here, then you're forced to then confront this dual problem, where you're trying to bound a t integral of zeta times this symmetric square. And it's a long interval here. It goes up to t over delta, but that's just all t's up to a certain range. It has this feature, like the longer you pick delta, or the bigger you pick delta, the shorter this dual moment becomes. So this is common in harmonic analysis. But pretty directly from this approach, or you can just use Cauchy-Schwarz on this integral and plug in our theorem, and what you get is that you can, in Xiaoxing Li's work, you can get Lindelof on average for delta as small as t to the 1 over 7. So she got 3 over 8. Various other authors improved it. I didn't write down whatever the state of the art was prior to our theorem, but now we can get 1 over 7. So I wrote this down in a slide. The argument's very simple, but just to be completely clear here, so we've got this dual moment we're trying to bound, like a first power of zeta times a first power of symmetric square. You can just use Cauchy-Schwarz. You'll get the second moment of zeta, which we have like the Lindelof on average bound for that from Hardy and Littlewood, so this is over 100 years old. But then we have to bound this second moment of the symmetric square. And so now you can plug in our theorem, so you get 4/3 for that, and you just do the algebra, and it's optimized when delta is t to the 1 over 7. So then that then gives you, so if you go back to her moment, so even if you apply this for the symmetric square L function in the t aspect, you can get good results on that. I mean, you also get bounds on the GL3 cross GL2 L function. But yeah, so applying that with the symmetric square L function, you get a better subconvexity bound. So you get 4 over 21. So now this is the best known subconvexity bound for symmetric square L functions in the t aspect. But yeah, it's just combining all of these methods together. Okay, what else? So just as a side comment, if you hear about all these symmetric square L functions and subconvexity and everything, so there's a well-known problem, which is the QUE problem, which is that one of the key components of this problem is to bound the symmetric square L function as f varies. So that this is kind of an opposite direction as this one up here. So the one in this corollary, f is fixed and t is varying. In this problem, the QE problem, t is fixed at basically 0 or other points, but just think of t as fixed at 0, and then you have to bound it as f varies. And so that's a lot harder, apparently, because we don't know how to do it. So another corollary is to the Rankin-Selberg problem. So to explain this corollary, so this is a famous problem, so a famous result of Rankin and Selberg going back to 1940, saying that the sums of squares of the coefficients of the GL2 cusp form satisfy an asymptotic formula that is some constant times x plus big O of x to the 3/5 plus epsilon. For a very long time, this gave the best known results on the size of these Fourier coefficients, because you can cook up a short interval on the left-hand side, basically of length x to the 3/5, and which you can get like the short interval just by taking the long interval at two different points and subtracting, and the main term basically cancels out. So you can get a good bound on a kind of a short sum over Fourier coefficients, and then dropping all but one term, you get a non-trivial bound on the Fourier coefficients. And so that was the state of the art for many, many decades. For individual bounds, and then even when we got better bounds, that the new bounds didn't come from improving this exponent in this problem. Anyway, so no one had improved on Rankin and Selberg's asymptotic formula until Bingrong Huang in 2021 improved this by basically, so the 3/5 he replaced by 3/5 minus 1/560, and he used some ideas from these delta method subconvexity results. But now we have a really simple proof of an improvement on this, which gives the exponent 4/7. So yeah, at least if it's a cusp form on SL2Z, but that should be extendable in general. But and the method is very simple. So if you ever want to sum up coefficients of some Dirichlet series, by like a Perron type formula, you can relate the sum to the integral of the Dirichlet series. And so what we're going to do is just take that formula, shift the contours over basically to the half line. So you hit a pole at s equals 1, that gives you the main term, and then on the half line you want to bound the Dirichlet series that you get that from these sums of squares, and that's exactly zeta times the symmetric square L function. And so the structure is almost identical to, I guess this one right here. So it looks like zeta times symmetric square with some kind of weight that might be oscillatory, but you just plug in absolute values and bound it with Cauchy-Schwarz. So it's the exact same argument as here. And if you just do that, just carry it out, it's completely standard, then and you plug in our result, then you get this exponent 4/7. Great. So that's that corollary. So now I wanted to talk a little bit about how the proof goes. So the first sequence of moves for a while follow what the previous authors did. So Agarwal, Lung, and Munshi on the short interval problem. So we follow those steps for a while, and then at some point we depart. So the beginning tools are completely standard. So first we'll use an approximate functional equation for the for the L function, so it says that the L function is, you can relate as a partial sum of the Dirichlet series up to the square root of the conductor, or really it's two sums that look like that, but we can just handle one of the two. They both behave the same way. So let's just look at that. And then, so we're going to plug that in, and then we have to average over the family. So we have to compute some kind of t integral with m over n to the it. So we should smooth out the integral, so that's what this weight function w is doing. So w is some kind of Schwartz class function. And so if you just do this computation, you get t times the Fourier transform at t log m over n. And since w is just a fixed Schwartz class function, so is w hat. And so that's saying, like, so if log m over n was like 2 or something like that, this would be w hat of 2 times t, and that's like t to the negative a million in size. And so really what's happening is this is saying log m over n has to be close to 0, or really like 1 over t, and that's going to say that m has to be really close to n. And this is completely standard for these kinds of t integral families. And so anyway, so to make this a little more precise, all you do is just take a little power series for log m over n, write it as log 1 plus m minus n over n, and then that's very close to m minus n over n because we have to be close to 1, and so yeah, so that's saying m minus n basically has to be at most like n over t, which is like square root of t. So m and n themselves are like t to the 3/2, but their difference is like square root of t. So the difference is quite small. Okay, so that's completely standard. This is always what these t integrals do. They just tell you that if you have a pair of integers, they have to be close by as real numbers. So if you just plug in the approximate functional equation and apply this family averaging, the t integral, that transforms our second moment into a sum of these coefficients. So these lambda f of n, those are the coefficients of the GL3L function. So we end up with these kind of sums of shifted convolution sums. So we've got a sum over n and a sum over k. So unfortunately, we don't know how to, it's unknown. It'd be, again, a sensation to get an asymptotic formula for the sum of d3n plus 1. And that's like the simpler version of lambda of n times lambda of n plus 1. And if you could do 1, then you should be able to do any fixed k. So we don't know how to solve this problem up here for a fixed k. So that's the bad news. But k has quite a lot of room for summation. There's around square root of t values of k. So we can try to exploit the sum over k to get some kind of cancellation. So that's I mean, we have to. Otherwise, well, I mean, if we don't, then we're solving this more famous problem of d3n plus 1. So so if we're not solving that problem, then we have to somehow use the sum over k. So we're going to solve or use this this DFI delta symbol to detect this, to detect that that these two integers are shifted by this k. So we have n and n plus k here. So we're going to use this DFI delta symbol. I have to imagine that probably this has been brought up in other talks, but anyway, maybe the notation is different. So there's a formula for the delta symbol as a sum of Ramanujan sums. You sum over the moduli, yeah. So d is some sort of junk variable for this talk. Just think of it as 1. So this is saying basically c goes up to q, and then you've got this extra second component that says that n over c times q has to be, like, it can't be too big. So we have these two variables. So this is supported on like both of these components, x and y, are sort of big O of 1, and this is some sort of smooth function. And this is the standard DFI delta symbol. Yeah, that probably is pretty well known in at this particular conference. So the standard, like out of the box choice for the delta symbol is to take q squared equals n. That's sort of like always the traditional choice, but there have been a lot of advances in the area where there's like more clever choices for these parameters depending on what your problem is, and so there's like a vast amount of work on this that again, like maybe you've seen, it's mentioned in some of the other talks. For this problem, again following the short interval method, we're going to choose q smaller than that. So what that's going to do is make, so q is smaller, that's going to make c smaller, and there's a trade-off. So you can make c smaller, but that's going to make this f function behave, like it's kind of going to push some oscillation into it. It's going to make it, so there's sort of like a kind of like an arithmetic conductor and an analytic conductor. The arithmetic conductor is being small, it's going to force the analytic conductor to be big. And so the Archimedean conductor in this problem should be around n over q squared. So if you make q small, that's going to make this Archimedean conductor in the delta symbol, it's going to make that part bigger. So what's an Archimedean conductor? So you should think of like a function like n to the iy as having Archimedean conductor around size y. And more generally, if you have some kind of oscillatory, like if you have some sort of phase function that's around size y and has nice derivatives, we should also think of that as having Archimedean conductor of size y. And like even more generally, you should think of if you have a function whose Fourier transform is essentially supported up to y, that should mean like it has Archimedean conductor of size y, because that's kind of like, if you go to the, like if you write f as, just use Fourier inversion on it and write f as an integral of f hat, it tells you like how big your t has to be in that integral, and that's kind of controlling the amount of oscillation of your function. Either with additive characters, or you could also do a Mellin transform version of this where you have multiplicative characters. It doesn't really matter. It's just a kind of a matter of taste, or depending on your problem, like which choice you might make about like additive versus multiplicative characters. So one of the principles here is that, so if you have two functions, they both have Archimedean conductor at most y, and then you multiply them, it still has Archimedean conductor at most y. This is just basically saying if you have two phases, they're both like size y, you add them, it's still like y. But if you contrast this, if you like have a periodic function mod q1 and you multiply it by a periodic function mod q2, that's going to have period, which is the least common multiple of q1 and q2. And if q1 and q2 are relatively prime, this is going to be gigantic. It'll be like the product, q1, q2. But if q1 and q2 are the same, then the period stays the same. The period does not get bigger. So it's very much similar to this kind of phenomenon. So once you already have some kind of conductor in some component, you're like kind of free to like multiply by something with that same conductor, and it won't increase the conductor in that component. I guess that's kind of the idea. So so that's the reason for allowing your delta symbol to have some Archimedean component, because in our problem we already have some Archimedean component. Like we're saying that, I mean, I guess there's different ways to think about this, but like, so the fact that like k is kind of small is saying these integers are small. It's kind of a short interval problem, which you can detect with harmonic analysis, and that's like saying that these are like there's some Archimedean component. I don't know. I'm a little vague. It's a little early in the morning for me to like explain this too precisely. But anyway, so there's some reason why you might think that there's some Archimedean component. Like this is a little bit clearer, I think, in the short interval work, because then you more clearly see this oscillation from the short interval, which you kind of don't see with the long interval, or at least you don't see as directly, but it's nevertheless still there. So anyhow, so if you apply this, the DFI delta symbol, our moment is exactly, so it started out, we had this shifted convolution, and so that's this first line, but then now you apply DFI, and you get a sum of Ramanujan sums with your Fourier coefficients and with your DFI weight function. So we're going to apply the GL3 Voronoi summation formula to both the sum over n and m. The GL3 Voronoi formula says you can convert an additive character with a parameter a to a Klosterman sum with parameter a bar. With some complicated integral transform and all that stuff, but that's the arithmetical shape of things. Just to compare or contrast, like the more well-known GL2 Voronoi formula says you can swap like an additive character with parameter a by an additive character with parameter negative a bar, where that's the multiplicative inverse mod c. So for the k variable, that's kind of a GL1 thing. Like there's no, like the k does not see these GL3 coefficients, and so we're just going to use Poisson summation in k. That's like the GL1 summation device. So you do those moves, and then to make a long story, a very long story short, you end up with an expression that kind of looks like this. So you've got so this y integral is kind of your Archimedean parameter. It goes up to n over q squared. That's our Archimedean phase that's built into the DFI method. We've got our same moduli as in DFI. Our dual value of k is, we'll call that capital K. So that's qt over n. And then on the inner sum, we've got a sum of length n prime. That turns out to be n squared over q cubed. And you've got the GL3 coefficients times this Klosterman sum with the bar in it. All of these dual lengths of summation come from the general principle that the dual length is the conductor over the original length, and you just do a little calculation and you see like how this plays out. Okay, so this is like structurally the same as what the short interval authors came up with, but the shape of this is changed now because somehow like the Archimedean part gets cleaned up by having a longer integral. And so this is like, yeah, I don't know. So this part, it is a bit different at this point, but in terms of the arithmetic, it's the same. Like in terms of the Klosterman sums and the coefficients and all that, it's the same kind of structure. So now, right, so here's a different way we could have proceeded, and this is actually how we proceeded for a while. So what you could do is you just take the formula that the previous authors did for the short interval, which was from like t to t plus delta. They got some kind of expression for this that's similar, but like this. So instead of like this integral being on the outside, they've got an integral on the inside with some complicated phase. And the phase depends on like delta and all the parameters in sight. And then what you can do is then sort of sum, so that's like t to t plus delta. Now do the same thing, but shift t by delta. So now you integrate from t plus delta to t plus 2 delta. And then do it again, t plus 2 delta to t plus 3 delta, and so on. And add up all of those things to cover the whole dyadic interval t to 2t. So you can do that. And then what we did in this, in these notes, or the earlier approach that we had, was we used Poisson summation to sum over those intervals and line them all up. And if you do that and like you clean it up, you end up with the same expression as this. So you get the same result in the end. So this turned out to be a little cleaner to just do it this way once and for all. So anyway, that's just a side comment since maybe that's of some interest. So then we're going to, okay, so now we've got this complicated thing, and so we're going to stop using any properties of these GL3 coefficients and use duality. Again, this is the same method that the short interval authors use. They use duality. So then we want to bound this norm. So when I see something like this, I'm just thinking like, okay, this kind of resembles. There's so many, like if you read Ivan Kowalski's book on bilinear forms, they have a chapter on these bilinear forms and the large sieve. Like they have all sorts of examples and like different variance on the large sieve, and this just to me looks like something you should try the large sieve on. Anyway, so okay, so that's So this okay. Sorry, I didn't. Okay, we haven't used duality. Yeah, I was getting ahead of myself. So the original expression, we've got the integral c and k on the outside and on the inside. But if you give up any properties of the coefficients, then you can use duality, and then you have to bound the dual problem, where n is on the outside, and then y, c, and k are on the inside. Okay. So now, what the previous authors did was, so that they used, so you square this out, use Poisson summation, and then they started using a recursive Cauchy-Schwarz argument, and then they used the Deligne bound. So we found an alternative route that doesn't follow those steps that I think is simpler in a lot of ways. But just, I guess as a side, before we head off into that, so I wanted to point out this for fun, I guess, that so if you assume like the best possible bound you could hope for this bilinear form, it's just there's like a standard thing that's like the number of things on the outside plus the number of things on the inside. If you just plug that in, like that best possible kind of norm bound, that would give you t to the 1 plus epsilon. So that would give you the sharp bound on the sixth moment of zeta. Okay, so this is great. So if you could bound this norm, if you could prove like the version of the large sieve for these kinds of expressions, you could get a Lindelof on average for the sixth moment of zeta. So needless to say, I don't know how to do that, but yeah. So this is actually, I think this is essentially what Ivich. So there's a paper of Ivich. It's kind of an interesting paper. It's in the conference proceedings. I don't know how well known it is. But he basically worked this out. So he used the DFI delta symbol. In this case, like the optimal choice would be square root of n, and that's the choice that he made. And he gets some kind of expression that kind of looks like this. And yeah, so this isn't like really, this particular observation I don't think is really new, although maybe it looks a bit different than what Ivich had. But I think the overall method is the same. Anyhow, okay, so that's just a side comment. So then now what we're going to do, so we did this Poisson summation in K, and we have this K on the outside, and after we do it like this, there's actually very little we can do with K, so we're just going to take it to the outside, although we did try to squeeze out some cancellation in the K variable as much as we could. So after you square out the sum and you apply Poisson summation, so it's Poisson summation mod C1, C2, you can evaluate the sum exactly. It's quite nice, and so at least in the kind of the case where C1 and C2 are relatively prime, you end up with this product of additive characters with inverses. This is okay. So this is this is just a fun calculation, and you can use this reciprocity, this standard additive reciprocity formula that lets you switch the modulus. So if you do that, it's a good thing because n times k becomes your modulus, and you get you'll get like a C2 C1 bar and then a C1 C2 bar. So this has two positive effects. So it reduces the period from C1 C2 to n times k, and also you get a function that only depends on this ratio of C1 over C2. So both C2 over C1 and C1 over C2, they only depend on the ratio. So this argument of this additive character only depends on the ratio. And so that means you can use multiplicative Fourier analysis to separate the variables C1 and C2 just in one go. This is just completely standard Fourier analysis, like multiplicative Fourier analysis. So you can write this additive character as a sum over Dirichlet characters with some coefficients, and you have chi of C1 and chi bar of C2. And the coefficient is just a twisted Klosterman sum. That's what this expression is. So if you just use this Fourier analysis as like finite Fourier analysis, you're going to end up with something that looks like this. So you have a sum over n, that's your moduli, you have a sum over characters mod nk, you have this Klosterman sum, and then you have this bilinear form or bilinear expression. So if we didn't have this G hat, this twisted twisted Klosterman sum, then this thing is perfectly set up to apply the large sieve inequality. Like we have good bounds on this. Okay, so we could bound the twisted Klosterman sum by a V-type bound, and if that's true, that we would get this basically 1 over square root of nk by this V bound. Unfortunately, the V bound is not always true for twisted Klosterman sums. I'm not sure how well known this is, but if you have a character, it might not always be true. Although in many cases it is. So like if your modulus is a prime, then it's true, and yeah. So that's like maybe the main case. But there are cases where it's not true, and this causes some problems. But we kind of know when it's not true, and we know, like, so it doesn't happen very often that the V bound doesn't hold, and we kind of understand like what's going on. So you can sort of control those failures of the V bound directly. So you just do that, and the optimal choice turns out to be square root of n over t to the 6th. And I guess this is just a kind of a technical comment. We could have kept k inside the square. We did the whole method with it that way for quite a while, and you get like all the bounds look different, but it turned out like the bound on the second moment at the very end was the same that we got by like kind of not doing anything interesting with k. And so having k like just be like a trivial variable on the outside made everything simpler, so we did it that way. But so anyways, that's just a I don't know, side comment. Another comment, so we only needed the Riemann hypothesis for curves via the V bound for these twisted Klosterman sums, whereas like the other method, the earlier method, used the Riemann hypothesis for varieties. Not that there's anything wrong with that, but it's just more complicated to do that. Another side comment, if you try to apply our method to sum over Dirichlet characters mod p, like twisted L functions, then it just doesn't work at all. But if you look at moduli that factor, like sufficiently factorable, then you might try to apply our method to that situation. And there's some work in progress on that, but I won't announce anything about this, but just to say there are people working on this. So then I'll just leave with just I think kind of an ill-posed question, which I'm just sort of curious about, which is when is this infinite or recursive Cauchy-Schwarz argument that was used in the short interval problem, when is that better or worse than a large sieve approach? And does this even really make sense to compare these things? In this particular case, we're able to do this large sieve approach, and for this long interval problem, we got a better result. But I think Joseph checked that like you should get the same thing if you kind of like. I guess ideally you should get the same bound using this infinite or recursive Cauchy-Schwarz for the long moment as you do for this large sieve approach, so you get the same thing. But what about other problems? Like, can you cook up a problem where there's no way to do a large sieve instead, or not? I don't know. So that's just something I'm curious about. So this particular instance, we're able to replace this interesting yet complicated argument with a large sieve. But are there other questions where you can't do that? So that's I'll just leave it with that and just say thanks for your attention, and sorry for going over a little bit.
Thank you. Any questions? Yeah.
I guess a natural question is if you managed to answer your earlier question about what's up with the short interval argument breaking down with long intervals.
So I think what happened was the Archimedean parts got really complicated, and they didn't really. I mean, maybe they weren't focusing on that part, but yeah, so I think, I mean, yeah, I don't, it's hard to say. I mean,
Fair enough.
yeah, Joseph might be able to give the best answer for that, but
Okay, I'll ask him next week. He's coming to visit
he,
Buffalo.
oh, okay, yeah. And I think he's giving a talk tonight.
Well,
Well,
that's true.
okay,
Also true. But
tomorrow for you. But yeah, he would probably have the best answer for that since he worked on both projects and can say it's hard for me to say like to talk about like why something didn't work on their end, but maybe
yeah, that's fair.
yeah, that might be good for him.
Thanks.
Any other questions?
Hi, Matt. So I was wondering this Rankin-Selberg problem, if you assume convexity, not convexity, like Lindelof for your L function, what bound do you get on the error term in the Rankin-Selberg problem?
Oh, I don't remember the bound you would
I
get.
guess my real question is that what's expected to be the truth, or is
Oh man. Well, you can always imagine. So okay, so if you shift to the half line, you'll get the like the you'll get the product of the L functions times some oscillatory weight, and then you might try to think there's some cancellation and additional cancellation and from coming from that. So you might hypothesize square root cancellation in that thing, and then maybe that would be the best you could hope for.
Okay, thanks.
But I don't know offhand like what you get, but that might be like the heuristic.
Hi, Matt. So in the last slide, second last slide on this last sieve, can you go there?
Yeah, let's see. This one?
Yes, yes. So which contribution will be large here? So for example, I was wondering if you average over K here as well, will that help in the large sieve step?
So okay, so the problem, yeah, we tried that first, and the problem is that so the problem is the trivial character. So when you want to use the large sieve with varying moduli, you need your characters to be primitive. And so like somehow like if G hat were extra small when chi was trivial, that would probably be okay, but it turns out like G hat is like, it's not particularly small when chi is trivial. That's just the classic Klosterman sum. And so so like if you ever want to do this, it's like you have to factor chi as like a trivial character times a primitive character, and then you can do the varying moduli large sieve with the primitive character parts, but not the trivial character parts. And so somehow it's like the trivial characters ruined everything. So that's why like summing over K didn't really help.
Okay.
I mean, you get some other bound, like you do get some bound, and it depends on your ranges of parameters. That it might be slightly better to do to put K in, but then for the second moment problem, it turned out you got the same final bound in the end, but the way you get there is different. So it's a little weird.
Yeah.
So there might be like for the bilinear, for the norm, like you might be able to claim bounds with K that we could have done that. We like maybe it didn't survive in the paper, but we had bounds like that at some point.
Okay.
Yeah.
And just to answer Anurag's question, so if you assume Riemann hypothesis, you get 1/2. So if you assume Lindelof hypothesis, you get 1/2, but the conjecture is 308 by Evich, I think, yeah.
So not 1/4.
Yeah, so 1/4 is for Dirichlet divisor, I think. Yeah,
Yeah.
yeah, for the Dirichlet divisor, that's 104. Yeah.
Okay.
Thanks.
Yeah, thanks.
Okay, any other questions?
You see me. Hello,
so
sir. How
that's-
are you?
Oh, hi, Sumendra.
Long time no see. Yeah.
Yeah, it's good to see you. I wish
Was
I
that your
was there.
DAS keyboard?
Yeah, it's there. I have two. I have one in my office.
I
and
know.
one
I
at
know.
home.
I know. All right. We'll catch up later
nice to
over
see
Zoom.
you. Yeah. Well, that sounds good.
Okay, let's thank Matt for a very nice talk.